This video will be used to demonstrate how you will solve what are called exponential equations. Before we can get into exponential equations, there are a few prerequisite skills that we're going to have to just review as we prepare to solve exponential equations, which on its own is really not that difficult to do. I'm just going to first go through some exponent work with you. The first thing that I'm going to look at is how do we change to a particular base. In this one, they've picked examples where I could change everything to be a power written as a base of 2. Now, in order to do that, you have to have numbers in here that are powers of 2. So, for example, if this is a 10, this isn't going to work. If this is a 24, this doesn't work. They have to be powers of 2. 2 to the 1, 2. 2 to the 2, 4. 2 cubed is 8. 2 to the 4th is 16. 32, 64, and so on and so forth. As you can see in all three examples, A, B, and C, the only numbers involved in the expressions are powers of 2. So the first thing I would do here is change the number 4 into its particular power of 2, which in this case is 2 squared. I'm going to change the 4 to be 2. There's 4 cubed. And now you have to remember your laws of exponents. If you have an exponent raised to another exponent, we refer to that as the power law. This would be 3 multiplied by 2, 2 to the power of 6. So 4 cubed is 64. 4 times 4 times 4, 2 to the 6 is equivalent to 4 to the third. It is also 64. This is a power of 2. That's a power of 4. 1 over 8. Well, 8 is 2 cubed. And exponent work says if we have an exponent in the denominator, it can jump to the numerator, and the exponent will just switch to a negative. So 2 to the negative 3 is 1 over 8. Now this one obviously has got a little bit more involved in it. Let's take 8 first, change it to a power of 2. 2 cubed to the exponent 2/3. Instead of square root, I'm going to use the exponent 1/2. Or actually, I could just do the square root of 16. Let's keep going this way. So I'm going to go 16 is 2 to the 4th. So that's 16. Square root is a half. And then 3 is cubed. 2 cubed raised to the 2/3. I multiply those exponents, so that would give me 6 over 3, which would be 2 squared. I've got 3 exponents here. I'm going to multiply them all together. So 4 times 3 is 12. Take half of 12. That's 2 to the 6th. Same base. We're multiplying. Add your exponents. Could have done that differently. So this is just a plan B to show you that you don't always have to do everything the way I do. In fact, plan B might even be better. 8 to the 2/3 means take the cube root of 8 and then square it. Well, the cube root of 8 is 2. 2 squared is 4. There's 8 to the 2/3. 16 is a perfect square. The square root of 16 is 4 cubed, which is 64. Well, 4 is 2 squared. 64 is 2 to the 6th. Multiplying, you add the exponents. There's a plan B. That also worked. Regardless, in all situations, we just have to make sure that we follow our laws of exponents. We'll eventually end up at the same place. All right, a couple more. It's always a fun one. I like to get students, if we were in the class, I'd say, okay, I want you to tell me which of the following is the biggest number. 4 to the 357, 8 to the 235, 32 to the 127, or 16 to the power of 180. And generally, it is crickets. Because the first thing students do is that it says no calculator. They'll try and sneak their calculator. But these are going to give you numbers that are so large that you can't even, the calculator will just say error because the numbers are too big, the calculator can't handle them. So then, typically students will end up stuck at this point. but then I'll give them a clue. I'll say to them, what if I had said 2 to the 10th and 2 to the 15th? And I said to you, which one is bigger? And then, of course, instantly everyone says, oh, it's 2 to the 15th. So how do you know? Because, well, they're both powers of 2. This means it's a number 2 multiplied by itself 10 times. This is a number 2 multiplied by itself 15 times, so this one's got to be bigger, which by mathematical reasoning is correct. I say, okay, there's your clue then. Look back at these. Oh, wait a second, look at the bases. They're 4, 8, 16, and 32. Those are all powers of 2. How about we just change everything so that we're comparing apples with apples instead of apples, oranges, bananas, and pineapples, all different bases. Look at this one. 4 is the same thing as 2 squared to 357. Multiply your exponents, you're going to get 2 to the 714. 8, 2 cubed to the 235. 235 times 3 is 2 to the 705. I think I've done that right. 32. 2 to the 5th to the 127. Oops, sorry. 2 to the 5th is 32. My exponent is 127. Multiply those together. That's going to be 6, 35. 2 to the power of 635. 16 is 2 to the exponent 4 to the 180, which is 2 to the 720. Now we've got 1, 2, 3, 4 different representations of these same original questions. However, all 4 of them now have a base of 2. 2 to that, that, and that. I can quickly now look and say, there's your biggest one right there, because it's the biggest power of 2. So there's a neat little way that exponents help us through that one, which even if you did have a calculator in your hand, it would not have been able to manage those numbers. Okay, so that was another look at positive exponents. These are just a couple like the one we had prior to that last slide, where I want you to, this one, I would like your answer to just be 5 is some exponent. That's your job. Figure out what is that exponent. Well, 25 is 5 squared to the 3. 125 is 5 cubed to the negative 3. 5 to the exponent 6. 5 to the negative 9. I'm multiplying, notice. And then if you're dividing, bases are the same. You subtract exponents. 6 subtract a negative 9 is 5 to the 15. All right, let's look at this one. This time I want everything to be powers of 3. And again, notice the numbers. 27, 9, 81, 243. You may say, I don't know what that is as a power of 3. Well, you have to figure it out. Use your calculator and take the, you might have to just go trial and error till you get 3 to some power that gives you 243. Pretty sure it's 5. 27 is 3 cubed. 5th root means 1/5. 9, 3 squared, so there's 9, cubed, and then to the 4th. 81, 3 to the exponent 4. Well, if you took 81 and multiplied by 3 again, that would give you 243, so that must mean that 3 to the 4 is 81. You must need one more power of 3. So 3 to the 5, there's 243 to the exponent negative 3. All right, let me see what I've got here. So I've got 3 to the 3/5. Multiply that by 3. 2 times 3 is 6, times 4 is 24. Here I've got 3 to the 4 multiplied by 3 to the negative 15. Add exponents, add exponents. So I'm going to do a bit of fraction work. 24 over 1. I want to be over 5 instead, so I got to multiply the numerator by 5. That's 120. So this would be 3 to the 123 over 5. The denominator is 3 to the negative 11. Now I got to subtract that exponent, subtract that exponent, and I will have my final answer. So I need 123 over 5, subtract a negative 11. Well, that's 123 over 5 plus negative negative. 11 over 1 is 55 over 5, which will get me up to 178 over 5. So that single expression, I have to type it in my calculator, and then go way back to the beginning and type all of this in my calculator. They should give me the exact same thing. They're equivalent expressions. One is written as a power of 3, a single power of 3. Nice, tidied up form. Check it if you don't believe me. Okay, so this will take us to where we want to introduce you to how to solve an exponential equation. If you kind of look at your toolkit of equations, you would have started out the first equations you ever solved were linear. Then you get into quadratic equations. Then you solved radical equations. We did a unit in trigonometry where we solved linear trig equations. We did quadratic trig equations. In fact, in this course, we've even done really ugly trig equations with different periods and bases or phase shifts and all kinds of stuff. Well, we're going to add to that now with what are called exponential equations. And I'm going to show you how to solve these. And again, this is for the most part quite straightforward. Based on the conditions we're working under this semester, we'll keep things pretty basic for you. And this is kind of what they call the principle of equality. And again, it really is almost self-explanatory. If I say b, being some base, a number, to an exponent, equals the same base to some other exponent, well, there's only one possible way that statement can be true, and that is if that exponent is the same as that exponent. So for example, at its most basic level, look down here at this. This is saying I have 2, so this would be like your b, and then over here it's the same base. These have to be the same. If this was a 2 and this is a 3, this doesn't work. However, because they're the same base, 2 to the x plus 6 is equal to 2 to the 5 only if the exponent on the left side was the same as the exponent on the right side. I'm just going to put this little symbol here, which hopefully you've seen before. Means therefore, 3 dots. Therefore, the exponent on the left has to equal the exponent on the right. Move your 6 over there. X has to be negative 1, which we can clearly see if I put negative 1 in here for x, which would be negative 1 plus 6, I would get 2 to the 5 equals 2 to the 5, and it would work. Now, what you got to make sure you understand is students will say, oh yeah, I see what he's doing. I'll put something like this, 3 to the 4x plus 1 equals 3 to the 2x minus 5. And say, solve this. I say, oh, I know how to start. You just divide both sides by 3. I'll say, really? What do you mean divide by 3? Well, I'm just going to divide by the bases. That is not what we are doing. We're using a mathematical principle of equality that states a base to an exponent can only equal the same base to that exponent if the exponents are the same. So here, 4x plus 1 would have to be equal to 2x minus 5 based on the fact that the bases were 3. I didn't divide the bases out. I just used mathematical reasoning to state that the only way this could possibly be true is if that exponent was the same as that exponent. And now you just solve it like a linear equation. So x would have to be 3. So let's check. If I put 3 in here, I'd get 3 to the 12. If I put 3 in, sorry, let me try that again. What did I do wrong? Oh, this should have been minus 6, which would make this a minus 3, not positive 3. Let me try that again. 4 times negative 3 is negative 12, plus 1 is negative 11. 2 times negative 3 is negative 6. Take away 5. That's also negative 11. So x equals negative 3 is in fact the solution to this exponential equation. All right, so we're going to look now at some exponential equations. All right, so let's take what we've hopefully accumulated over the last few slides and see if we can put that all together and solve this equation that we're staring at. Well, first of all, I recognize and say this is what we call an exponential equation. Now, I may have got ahead of myself. I started solving them on the last slide without really telling you the correct name of them and how you know that they're called that. Well, it's really easy. The unknown I'm trying to solve for is the variable x. Where is the variable x? It's in the exponent. So when your unknown is in the exponent, we call them exponential equations. So this would be an exponential equation. Well, the way I try and solve exponential equations is to try and get everything to be the same base on both sides of the equation. Look at this one, you've got a 9 and a 3. Well, 9 and 20, or sorry, 9 and a 27, getting ahead of myself. 9 and 27 are both powers of 3. Change the 9 to 3 squared. Leave your exponent as it is. Change the right to 3 cubed. Use your laws of exponents. Laws of exponents says when you have an exponent and you raise it to another, you multiply those together. And we're at the point we just discussed on the last slide. I have base 3 to this exponent equals the same base to another exponent over here. Well, the only possible way that this statement could actually ever be equal would be if the exponent on the left was actually the same as the exponent on the right. Then that statement would be true. So I'm just going to figure out what will make that happen. 4x would equal 13, divide by 4, divide by 4. If x was 13 over 4, that would be the solution to that exponential equation. If you're a steps kind of person, this is what you do. You get each side to always be the same base, then you compare the exponents, then you solve that equation. So let's take this one, for example, 5 to the x. Can't do anything else with that, but I can change 25 to 5 squared. If it's 5 squared in the denominator, right, so 1 over 5 squared, well, that's the same thing as 5 to the negative 2. 5 to the x equals 5 to the negative 2. Well, that one's really easy. As long as you know laws of exponents, x would have to be negative 2 because bases are 5, exponents have to equal each other. 81 and 27. Now you'll notice that it doesn't come out and tell you what to write the bases to. You've got to look the numbers over and pick out the correct bases. Well, 81 and 27 are powers of 3. 81 is 3 to the exponent 4. 27 is 3 to the exponent 3. Left side is 3 to the 4. Multiply. There you go. Now, I have what we always are trying to get, 3 to an exponent equals 3 to an exponent. Therefore, the exponent on the left has to be the same as the exponent on the right. Let's bring the 3 this way. So 7 is equal to 9x. 9 divided by 9. 7 over 9 would have to be your solution to that one. Well, we look at this one and say, wow, that's easy. Look, they already have 5 to an exponent equals 5 to an exponent. Great. The only catch this time is the exponent on the left is quadratic. So therefore, when I do my bases are the same, exponents have to equal each other. So therefore, x squared, subtract 3x, is equal to 2x minus 4. So what this will now combine is make sure we remember how to solve a quadratic equation because it has an x squared in it. Quadratic equations, you got to make them equal to 0. You always want, you don't have to, but I highly recommend you get your x squared to be positive like it is here. So I'm going to move everything this way. Bring my -4 over. Most of the time, as you're doing radical equations, sorry, not radical equations, as you're doing exponential equations, you will get quadratics that'll factor. You probably won't have to use the quadratic formula. However, in theory, you could get to here, it doesn't factor, you'd have to go and try the formula. However, this one will factor. Multiply to get 4, and add to give you -1. The numbers would be x take away 4, and x take away 1. So this bracket is multiplied by this bracket, and the answer is 0. Well, the only way to multiply and get 0 is if one of the brackets is 0. So you say, well, x was 4 would make the first bracket 0, and if you put a 1 in the second bracket, you would get a 0. There's your two possible answers for this one. X could be 4, or x could be +1. Unlike, I kept a couple times now I've referred to radical equations. I have that in the brain. That was the last type we did. Here, you don't have to verify like you do with radical equations. That's only a step where you look for extraneous roots when you're dealing with radical equations, but not with these ones. You don't have to verify these. If you had time, you could. You don't have to. Okay, we're starting to roll here. I got a few more. They're a little bit more difficult, and then that's it for radical equations. That's it for exponential equations. Well, if I look at the first one, 4 and 8 are almost together. The bases are not all the same, so I couldn't use laws of exponents. You can't multiply these together because then you'd be multiplying before you deal with exponents. You'd be breaking order of operations. You can't do that. So your only option is get everything. These, if you notice, are all powers of 3. 2 to the x plus 1. 4 is 2 squared to the x plus 1. 8 is 2 cubed to the x plus 1. And 128 is 2, let me think, 5, 6, 2 to the 7th. Use your laws of exponents on each of these. So multiply. That. Now the bases are the same, unlike up here where they were different. They're all powers of 2. Now you can add the exponents. X, 2x, there's 3x and 3 more x's, that's 6x. I got 1, a 2, that's 3, plus 3 more, that's plus 6, equals 2 to the 7th. The only way this could possibly be true would be if the exponent on the left side was equal to the exponent on the right side. Solve this equation. X has to be 1 over 6. So still not very difficult. 1/9, 1/27. A couple ways to do this. I think I'll change the 9 to 3 squared. To the x subtract 2. I'll change 27 to 3 cubed. To the x plus 2. Then I'll go, and as I said, there's other ways to go about this. I'm going to take my 1 over 3 squared and change it to 3 to the negative 2. To the exponent x minus 2. Change my 1 over 3 cubed to 3 to the negative 3. To the x plus 2. Multiply my exponents. Negative 2x plus 4. Negative 3x subtract 6. And I'm at that lovely spot we always like to end up at, where I get a base to an exponent equals the same base to a different exponent. The only way that can possibly be true is if these two exponents turn out to be equal to each other. So I figure out what x value will make that happen. Bring that x over here, bring that number over there, and there you have it. X would have to equal negative 10. I got one more little one I want to show you, I think. So there's a series of them here that I usually get students to kind of practice on your own. So I think I'll uncover the solutions. I'm going to do one of them though. Should answers to those ones. Forgot I had done this neat little trick. Had Mr. Holland show me this trick. All right, those are your answers for this one. Let's take this one down here. It'll throw students off sometimes. I'll take the. You can try any of these other ones. The answers are there if you just want to practice. I'm not going to go through all of those. But I'm going to go through D2 to the 2x plus 2 plus 7 equals 71. So right away, students get a little puzzled with this one. They say, there's a couple of things. This is the very first one that has addition mixed in there anywhere. Because the problem with addition is that there's no laws of exponents for adding and subtracting. There's only laws of exponents for multiplication, division, and powers of powers. So this right here is going to be a problem. The other problem that if you look at it, 7 and 71 are definitely not powers of 2. In fact, they're both prime numbers. The only thing that divides into 7 is 7 and 1. The only thing that divides into 71 is 71 and 1. If I leave this as it sits, I'm in trouble. But if I just cleverly make one little adjustment, which would be just take away 7 from both sides. If you do that, you're going to end up with 2 to the 2x plus 2. 71 minus 7 is 64. Now, isn't this a lot better? I don't have any addition mixed in the middle of it, or subtraction. I don't care about exponents. I'm talking about down here like this one. And 64, unlike these numbers, is a power of 2. Now we're in business. Change 64 to its corresponding power of 2. 2 to the exponent 2x plus 2. 64 is 2 to the exponent 6. These exponents have to equal each other. 2x plus 2 would have to be 6. And just a bit more room here. Keep solving. 2x would have to be take away 2 from both sides. Divide by 2. Divide by 2. X would have to be 2. There's your final answer. Let's suppose I gave you 24 equals 3. And here I have 32 to the x plus 7. I suppose I had that. And I was trying to solve for x. Now this one, students might look at and say, well, it doesn't have any adding and subtracting, so that's not the issue. But 24 and 3, well, this isn't going to work. They're not powers of 2. I can't do it. I quit. Too hard. Won't work. Think. Use your mathematical reasoning skills. How about if I clean up the right side a little bit and just, now you can't, here's what students do wrong. They multiply 3 by 32. As soon as you do that, you're breaking order of operations. You're multiplying before you ever deal with an exponent. You can never multiply those together when there's an exponent up there. But what you can do is divide both sides by 3. Now watch this one little ingenious step and how much it cleans things up. Guess what? 8's now a power of 2. 32 is a power of 2. Off we are to the races. 2 to the 3, 2 to the 5, to the exponent x plus 7. Multiply. So now the exponent on the left has to be the same as the exponent on the right. Rearrange. So I'm going to bring that over here. I would get negative 32 is equal to 5x. Divide both sides by 5. That doesn't reduce, so I'm just going to leave it as negative 32 over 5. Would have had to be my x value to make that exponential equation work out. Okay, so those last two just had a couple of little rearranging you had to do first, but all of the equations you're going to be presented in this class, you're going to be able to rearrange and get them to be a base to an exponent on the left side, and then the same base to some exponent on the right side. And then you'll set the exponents equal to each other. If that's not happening, something went wrong. Go back and recheck your steps, or is there some rearranging you haven't done that could allow it to happen? but somehow you're going to be able to change everything to common bases. So that is my explanation of how to solve uh, exponential equations where they can all be changed to the same basis. Later on in this unit, we'll look at the scenario where you can't. So let's suppose you have 7 to the x plus 3 equals 10 to the 2x. You can, in fact, solve that, not with this strategy, but with another strategy I'll teach you later on. All right, so I'm just going to put up some questions here from your book that you can look at on page 364, numbers 1 through 5. You can anticipate an assignment over the next day or so where I will go back and first ask you a question about exponential functions, their properties, asymptotes and y-intercept and all that good stuff. And then we will give you a couple of exponential equations to solve along with it. Okay, so you'll see that coming over the next day or two. Keep an eye on your Teams for notifications. Good luck.